I think the screen is visible. So, shall I start?
Yes, sir.
Yes, sir.
So, we are discussing uh, your rank of a matrix. Let us discuss Gauss elimination and back substitution. And in your rank, you can see here that it is also an elimination method where two rows are being there and the other rows are having all the elements 0 and the rank is 2. Similarly, to solve a matrix also, the elimination method is very much helpful, and Gauss elimination is one of the very interesting elimination method by which we can have our back substitution and solve the matrices and thereby the system of different system of equations. So linear systems that proceeds systematically irrespective of particular features of the coefficients, and we can solve them by using standard elimination method, and it is a method of great practice in great practical importance and is reasonable with respect to computing time and storage demand. So if the system is in a triangular form, say 2x1 plus 5x2 is equal to 0 and 13x2 is equal to minus 26, then we can solve it by back substitution. We can solve it by back substitution. And what is back substitution? Solve the last equation for the variable x2 is equal to minus 26 by 13 is equal to minus 2 and then work backward. Okay. So in the second equation, you have your 13x2 is equal to minus 26. So your x2 is equal to minus 26 by 13. That is equal to minus 2. So by putting the value of x2 in the first equation, your 2x1 plus 5 into minus 2 is equal to 2. So 2x1 minus 10 is equal to 2. So 2x1 is equal to minus 8 and your x1 is equal to minus 8 by 2 is equal to minus 4. Sorry, here it is 6. How it is 6? Your x2 is equal to minus 2. So your minus 2 multiplied by 5 is equal to minus 10. Okay, minus 10, when it go to right hand side, it will become plus 10. So your 2x1 is equal to 2 plus 10 is equal to 12 and your x1 is equal to 6. That is 12 by 2. Okay. So if you have an elimination type of thing, then you have an equation where there is only one variable, and you can have the value of that variable from that simple equation. You can put that variable in another equation, and you have got you can get another variable. Then by putting the value of these two variables, you can have the third variable, value of third variable, and so on and so forth, and you can solve the equations, and you arrive at the solution of the system of equations, and you have your value of all the variables very elegantly. So let us have another equation which is not in a triangular form. So 2x1 plus 5x2 is equal to 2 and minus 4x1 plus 3x2 is equal to minus 30. And your augmented matrix A will be 2, 5, 2, minus 4, 3, minus 30. We leave the first equation as it is and we have to uh, uh, eliminate some of the uh, positions in the matrix and arrive at a simpler equation. So let us eliminate x1 from the second equation. To get a triangular system, uh, for this we add twice the first equation to the second, and we do the same operation on the rows of augmented matrix. And this will give you minus 4x1 plus 4x1 plus 3x2 plus 10x2 is equal to your is equal to minus 30 plus 2 multiplied by 2. So your 13x2 is equal to minus 26. x1 is being eliminated, and you are being with 2x1 plus 5x2 is equal to 2, and 13x2 is equal to minus 26, because x1 is being eliminated by adding row 2 with 2 multiplied by row 1. So your augmented matrix will now become 2, 5, 2, 0, 13, minus 26. So now you have the now you have the eliminated one, that is two equation in two unknowns, giving the triangular form, from which back substitution you can have, and you can have your other value of other variables. So you have your x2 is equal to how much? Minus 2, by putting it in the previous equation. Back substitution. Substitute this value uh, in the previous equation by going backward, and you'll have your x1. Are you getting it? So where row 2 plus 2 row 1 means add twice row 1 to row 2. So let us consider a linear system of n equations in n unknowns. That is x1 so on so forth. xn is a set of equations u1 so on so on so forth en of the form a11 x1 plus so on so forth a1n xn is equal to b1, a21 x1 plus so on so forth plus a2n xn is equal to bn, and an1 x1 plus so on so forth ann xn is equal to bn. So the first equation is your e1, second e2, and last one is en. So the coefficients a, j, k, and the bj are given numbers. The system is called homogeneous if the bj's are zero, otherwise it is called non-homogeneous. So using matrix multiplication, please mute it. So using matrix multiplication, we can write a singular a single vector equation, that is Ax is equal to b, as shown in the screen. So you have to eliminate some of the positions in the matrix A by rearranging the columns or with simple arithmetic, as I have discussed earlier. So the matrix, the augmented matrix of the equation is A11 so on so forth, N1, B1, A21 so on so forth, A2 and B2, N1 so on so forth, ANN, BN. So now the solution is a set of numbers x1 to xn that satisfy all the n equations. And a solution vector of this is a vector x whose component constitute the solution of that matrix or that vector. So the practical method for solution of linear system is the Gauss elimination. So we can reduce a given system to triangular form, and is it possible to reduce all these type of equations in triangular form? This is a pertinent question. And in the first step, we eliminate x1 from the equation e2 to en, and we do this by adding or subtracting suitable multiples of e1 from equation e2 to en, and taking the resulting equation called e2 star so on and so forth en star as new equations. So the first equation is called the pivot equation, and in this step a11 is called the pivot. This equation is left unaltered. You can you try your best not to alter the first equation, and the first coefficient a11 is called the pivot. This equation is all left unaltered. The second step, we take the new second equation e2 star, which is no longer contains x1. Similarly, E3 star no longer contains E1 and X1 and X2, so on and so forth. After n minus 1 steps, this gives a triangular system that can be solved by back substitution. In this way, we obtain precisely all solution of the given system. The pivot AXX or AKK in step K must be different from 0 and should be large in absolute value to avoid round of magnification by the multiplication in the elimination. For this, we choose our pivot equation 1 that has the absolutely largest AJK in column K and on or below the main diagonal, actually the uppermost if there are several such equations. This popular method is called partial pivoting. Total pivoting involves both rows and columns interchanged, which is highly used in practice. So let us have an example so that you can better understand how we can solve system of equations by using back substitution or Gauss elimination or partial pivoting. So the system of equations are like this as shown in the screen. 8x2 plus 2x3 is equal to minus 7. 3x1 plus 5x2 plus 2x3 is equal to 8. 6x1 plus 2x2 plus 8x3 is equal to 26. So we have to pivot since E has no x. अब E first equation में there is no x term. So in equation E2 has the largest coefficient. By interchange of E1 and E3, you can have your 6x1 plus 2x2 plus 8x3 is equal to 26, and your 3x1 plus 5x2 plus 2x3 is equal to 8, and 8x2 plus 2x3 is equal to minus 7. So you must retain your pivot, which is not in the original equation. So in the modified equation, your 6 is A11, which is the pivot. Now step 1 is elimination of x1. So how can you do it? So the pivot is 6x1 and you have to eliminate 3x1 as shown in the screen. For this, you have to subtract half times the pivot equation from the second equation, and the result will be your 6 2 8 0 4 minus 2 0 8 2, and b1 b2 b3 will be 26 minus 5 and minus 7 as shown in the screen. Now x1 is being eliminated in the second and the third row. Then the next one is elimination of x2. You can you have your pivot here as 8x2 and you have to eliminate 4x2. Okay, to eliminate x2 from the third equation, you have to subtract 1 by 2 times the pivot equation from the third equation, and the triangular result in triangular system is now your 6 to 8 26 0 8 2 minus 7 0 0 minus 3 and minus 3 by 2. And from this system, you see in the third row there is only x3, and you can solve this equation very easily. So your minus 3x3 is equal to minus 3 by 2. So your minus x3 is equal to minus half, and by putting the value of minus half in the second equation, you can have your value of x2 as minus 1, and by putting the value of x2 and x3 in the first equation, you have your value of x1 as 4. Are you getting it? Am I audible?
Yes, sir.
If you have any doubt, you can ask. Okay, similarly, you can solve this system of equation also. X1 minus x2 plus x3 is equal to 0, minus x1 plus x2 minus x3 is equal to 0, 10x2 plus 25x3 is equal to 90, 20x1 plus 10x2 is equal to 40. So your pivot is now x1, and you have to keep the first equation, that is x1 minus x2 plus x3 is equal to 0, intact, and you have to eliminate the other equation so that it will make a triangle as this, that is minus 1 minus 1 1 0 0 10 25 90 0 0 minus 95 minus 190 0 0 0 0. So now it is having a triangular form, and your in the third equation you have minus 95 x3 is equal to 190. So your x3 is now minus 2. If by putting the value of x3 in the second equation, 10 x2 plus 25 x3 is equal to 90, you have your x2 is equal to 4. And by putting the value of x2 and x3 in the first equation, you have your x1 is equal to 2. Then Gauss elimination of where infinitely many solutions exist. This is shown in the example. You can try it. Then Gauss elimination if no solution exists. That is also a special case. Then your elementary transformation. Any one of the following operation on a matrix is called elementary transformation. By interchanging any two rows or columns, this transformation is indicated by R, I, J if the ith and jth row are interchanged. And multiplication of the element of any row or column by a non-zero scalar quantity to get K or J. Then addition of constant multiplication of the elements of any row to corresponding elements of any other row, Ri plus K or J. Two matrices are said to be equivalent if one is obtained from the other by elementary transformation and the symbol as shown in the screen is used for the equivalence. So there is another example, reduce the following matrix to upper triangular form or echelon form. So it is also it can be done by the same method we have adopted in Gauss elimination, and there are transformed into a unit matrix where the diagonal elements will be 1 1 1. Okay, by interchanging rows and columns and simple arithmetic. Then elementary matrix. A matrix obtained from a unit matrix by a single elementary transformation is called elementary matrix, and it is written as I is equal to in matrix 1 0 0 0 1 0 1 0 0 1. Okay. So every elementary row transformation of a matrix can be affected by pre-multiplication with the corresponding elementary matrix. So a matrix A is equal to 2, 3, 4, 5, 6, 7, and 3, 5, 9, and you can have your elementary matrix as 1 0 0 0 1 0 4 0 1 0 1, and you can show that every elementary column of matrix can be affected by post multiplication with the corresponding elementary matrix. To compute the inverse of a matrix, you can use Gauss-Jordan method, and it is P is equal to A to the power minus 1 or A inverse. The elementary transformation are to be transformed so that the property of being symmetric is preserved. This requires that the transformation occurs in pairs. A row transformation must be followed immediately by the same column transformation. There is an example. Use Gauss-Jordan reduction method or elementary matrix method to compute the inverse of a matrix. So the matrix is 3 minus 3 4, 2 minus 3 4, 0 minus 1 1. So now elementary row transformation which will reduce A to IA to I is equal to PA, then matrix will be inverse of that matrix. For that you write 3 minus 3 4, 2 minus 3 4, 0 minus 1 1 is equal to I, that is 1 0 0 0 1 0 0 0 1 multiplied by A. So then you have your 1 by 3 R1. So you will have your 1 minus 1 4 by 3, 2 minus 3 4, 0 minus 1 0, 0 minus 1 1 is equal to 1 by 3 0 0 0 1 0 1 0 0 1 multiplied by A. Then you subtract 2 R1 from R2, and you have your 1 minus 1 4 by 3, 0 minus 1 4 by 3, 0 minus 1 1 is equal to 1 by 3 0 0 minus 2 by 3 1 0 0 0 1 multiplied by A. Then you write minus R2. So then R1 plus R2, and in the third column R3 plus R2. Then your minus 3 R3 in the second column, second row. Then R2 plus 4 4 by 3 R3 in the second row. So you have your 1 0 0 0 1 0 0 0 1 is equal to 1 minus 1 0 minus 2 3 minus 4 minus 2 3 minus 3 a. So now you see that in the left hand side you have I, in the right hand side you have PA, that is A inverse A. So your A inverse will be 1 minus 1 0 minus 2 3 minus 4 minus 2 3 minus 3. Are you getting it? By rearranging the values in the rows and columns such that the left hand side will be an unit matrix, that is I. You have your A already, and the matrix which is multiplied by A will be A inverse, and this is done by this Gauss Jordan method. Then there is another example, you can go through it. Then another example, A is equal to 2 4 3 2 3 6 5 2 2 5 2 minus 3 4 5 14 14. You see, in all these, your last expression will be AI, that is nothing but P or A inverse, because A inverse is equal to I. So Gauss Jordan method uses this technique to find out the inverse of a matrix. Linear dependence of vectors and n-dimensional space. Two non-zero two-dimensional vector A is equal to A11, A12 is not equal to 0. Then your A2 is equal to A21, A22 is not equal to 0 are defined to be linearly dependent if two numbers x1 and x2 can be found that are not both 0. So that the linear relation x1 a1 vector plus x2 a2 vector is equal to 0 holds. They are linearly independent if x1 is equal to 0 is equal to x2 is the only solution of this linear relation. Okay, you can write it in Cartesian system or any other coordinate system. Then Gram-Schmidt procedure. In an n-dimensional vector space with an inner or scalar product, we can always construct an orthonormal basis of n vectors wi with wi dot wj is equal to del ij, which where del ij is the Kroneker's delta, starting from n linearly independent vectors vi, where I is equal to 0 1 to so n minus 1. Okay, so this is the procedure. We start by normalizing V0 to unit by defining W0 vector is equal to V0 vector by root over V0 vector, and then proceed to have the solution. Then there are an example by which you can realize how Gram-Schmidt orthogonalization takes place. Okay, so you can go through these as shown in the screen. Orthogonal polynomial generated by Gram-Schmidt orthogonalization, un, which is a function of x, is equal to x to the power n, where n is equal to 0 1 2 are shown in the screen. Legendre, shifted Legendre, Chebyshev 1, shifted Chebyshev 1, Chebyshev 2, Laguri, associated Laguri, and Hermite. Okay. So the interval for Legendre -1 smaller equal to x smaller equal to 1, and for Hermite minus infinite smaller than x smaller than infinite. The weighting function for Legendre 1, shifted Legendre 1, Hermite e to the power minus x square, and the standard normalization for Legendre is integration -1 to 1 pn square dx is equal to 2 by 2n plus 1, and for Hermite it is 2 to the power n pi to the power half n factorial, the integral. Okay, it is shown in the screen, you can go through it. Then eigenvalues and eigenvectors in quantum mechanics, which I shall teach you from tomorrow. We come across the following type of equation. Q cap psi is equal to small q psi. So Q cap ket q is equal to q ket u. So in equation, Q cap is an operator and Q are scalars. Psi is called the eigenfunction of the operator Q cap belonging to the eigenvalue Q. And these operators can also be written in a matrix form. So Q, ket Q is the eigenvector of Q cap belonging to eigenvalue Q. These equations are called eigenvalue equations. In quantum mechanics, we represent operators by matrices. The matrix form of an eigenvalue equation is A is equal A, which is a function of x, is equal to lambda x. where A is a square matrix and X is the eigenvector of matrix A belonging to the eigenvalue lambda. So you can write Ax is equal to lambda Ix, and your A minus lambda I multiplied by X is equal to 0. So in a matrix form, you can have your A is equal to A11, A12, so on so forth, A1n, A21, A22, so on so forth, A2n, A so on so forth, AN1, AN2, so on so forth, ANn, and I will be a diagonal matrix having diagonal values 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. So from the secular equation or characteristic equation, you can solve it and get the eigenvalues. That is your A minus lambda I. Then eigenvalue of a diagonal matrix. So in diagonal matrix, only diagonal terms exist and all other terms you cannot find here. Properties of eigenvalue: a square matrix A and its transpose have the same eigenvalues, and the proof is shown in the screen. The sum of eigenvalues of a matrix is equal to the trace of the matrix. Okay, so trace of the matrix, that is lambda 1 plus lambda 2 plus so on so forth, the lambda n is equal to trace of A. Then so there are some examples. You can go through these as shown in the screen. Then application of Cayley-Hamilton's theorem. One can determine the inverse of a non-singular matrix using Cayley-Hamilton theorem. If the matrix satisfies the theorem, then Cn a to the power n, Cn minus 1 a to the power n minus 1, so on so forth, C1a plus C0I is equal to 0. Left multiplying this equation by A inverse, you can have your Cn a to the power n minus 1 plus Cn minus 1 a to the power n minus 2, Cn minus 1 a to the power n minus 2 plus so on so forth, C1I. So your A inverse is equal to minus 1 by C0 multiplied by Cn a to the power n minus 1 plus Cn minus 1 a to the power n minus 2 plus so on so forth, Cii. And the higher positive integral powers, if it can be computed using Cayley-Hamilton theorem, if A satisfies Cayley-Hamilton theorem, that is Cn a to the power n plus Cn minus 1 a to the power n minus 1 plus so on so forth, C0I is equal to 0. Left multiplying by A, we get Cn a to the power n plus 1 plus Cn minus 1 a to the power n plus Cn minus 2 a to the power n minus 1, so on so forth, C0a is equal to 0. So a to the power n plus 1 is equal to minus 1 by Cn, Cn minus 1 a to the power n, Cn minus 2 a to the power n minus 1 plus so on and so forth, C0a. So we thus conclude that any positive integral power of a non-singular matrix A can be expressed as a linear combination of those of lower degree. So there is an example. Verify Cayley-Hamilton theorem for a matrix A is equal to 1, 2, 3, 4 and use it to find A inverse. So your determinant of A will be 1 multiplied by 4 minus 3 multiplied by 2 is equal to minus 2, and it is not equal to 0. So your A inverse exists. So the secular equation will be A minus lambda I is equal to 0. So 1 minus lambda 2, 3, 4 minus lambda is equal to 0. So your 1 minus lambda multiplied by 4 minus lambda minus 6 is equal to 0. So your lambda square minus 5 lambda minus 2 is equal to 0. And by Cayley-Hamilton theorem, A itself obeys the above equation if lambda is replaced by A. So your lambda is replaced by A, and you can write A square minus 5A minus 2I is equal to 0. And your if you write A, then 5 and A matrix minus 2 matrix, you can find that it is 0, 0, 0, 0, and your Cayley-Hamilton theorem is verified. Then you can find out inverse of A as shown in the screen. Verify Cayley-Hamilton theorem for the matrix. Okay, by similar method you can have it. Determination of A inverse, you can see by using Cayley-Hamilton theorem. You can also determine A inverse by following the method. Here is an example. Let's go through it. Then your x is equal to x plus by and y is equal to cx plus dy. So capital X, capital Y matrix is equal to ABCD multiplied by xy, or R is equal to MR, where A, B, C, D are constants. For every point x, y, this equation gives us a point x comma y. If we think of each point of x comma y plane being moved to some other point, with some points like the origin not being moved, we can call it process, call this process mapping or transformation of the plane into itself. All the information about this transformation is contained in the matrix M. So we can say that this matrix is an operator which maps the plane into itself. Any matrix can be thought as an operator on conformable column matrix R. Okay, so the matrix M is a linear operator, and we have one set of coordinate axes, and the vector R has been changed to the vector R vector by the transformation as shown here. So we have two sets of coordinate axes x comma y and x dash y dash, and one vector R is equal to R dash vector with coordinates relative to each set of axes. This time the transformation as shown in the figure tells us how to get components of the vector relative to the axis when we know its components relative to axis x comma y. Then similarity transformation. Consider the transformation equations capital X is equal to qx dash and capital Y is equal to qy dash, where xy are two different vectors in the basis E and x dash y dash are two different vectors in the basis E dash. So your Q is a non-singular matrix. So your x dash changes to x and y dash changes to y by the column matrix Q. So you have your x is equal to ay, where A is a non-singular matrix. This equation implies that y changes to x in the same basis by the matrix. Combining these two equations, we can write qx dash is equal to ay is equal to aqy dash, and your q inverse qa dash is equal to q inverse aqy dash. So your I x dash is equal to q inverse aqy dash, and your x dash is equal to by dash, and your b is equal to q inverse aq. So this implies that b is equal to q inverse aq changes the y dash into x dash. We thus observe that b changes y dash into y in the same way as a changes x dash into x. We say that b is obtained from a by a similarity transformation. Q inverse is equal to q inverse aq q inverse is equal to IAI. So A is equal to Q inverse, and we can write P inverse is equal to Q, then A is equal to P inverse B T. So A can be obtained from B by a similarity transformation. So you obtain similar matrix, thereby two matrices A and B are said to be similar if there exists a non-singular matrix Q such that B is equal to Q inverse AQ. Two similar matrices have same eigenvalues, and the proof is shown in the screen. You can go through it, and if you have any doubt, you can ask. Then diagonalization of matrix is another important thing. If a square matrix A of order small n has n linearly independent eigenvectors, then a matrix P can be found such that P inverse AP is a diagonal matrix. So the proof is like this. We shall prove the theorem for a matrix of order 3. The proof can be easily extended to matrix of higher orders. So your A is equal to A1, B1, C1, A2, B2, C2, A3, B3, C3. And let lambda 1, lambda 2, lambda 3 be its eigenvalues, and x1, x2, x3 the corresponding eigenvectors, where your x1, x2, and x3 are can be written as shown in the screen. X1 is equal to x1, y1, z1, x2 is equal to x2, y2, z2, x3 is equal to x3, y3, z3 matrix. So for the eigenvalue lambda 1, the eigenvector can be written as a1 minus lambda 1 multiplied by x1 plus b1 y1 plus c1 z1 is equal to 0. Similarly, your a2 x1 plus b2 minus lambda 1 y1 plus c2 z2 is equal to 0. Similarly, your a3 x1 plus b3 y1 plus c3 minus lambda 1 z1 is equal to 0. So we have a1 x1 plus b1 y1 plus c1 z1 is equal to lambda 1 x1. A2 x1 plus b2 y1 plus c2 z1 is equal to lambda 1 y1. Similarly, a3 x1 plus b3 y1 plus c3 z1 is equal to lambda 1 z1. Similarly, for lambda 2 and lambda 3, we have a1 x2 plus b1 y2 plus c1 z2 is equal to lambda 2 x2. A2 x2 plus b2 y2 plus c2 z2 is equal to lambda 2 y2, and a3 x3 plus b3 y2 plus c3 z2 is equal to lambda 2 z2. Similarly, your a1 x3 plus b1 y3 plus c1 z3 is equal to lambda 3 x3, a2 x3 plus b2 y3 plus c2 z3 is equal to lambda 3 y3, and your a3 x3 plus b3 y3 plus c3 z3 is equal to lambda 3 z3. So we consider the matrix P is equal to x1, x2, x3, y1, y2, y3, z1, z2, z3, whose coulombs are eigenvectors of A. So you can write AP is equal to A1, B1, C1, A2, B2, C2, A3, B3, C3 multiplied by x1, x2, x3, y1, y2, y3, z1, z2, z3. So you can write A1, x1 plus B1, y1 plus C1, z1, A1, x2 plus B1, y2 plus C1, z2. A1 x3 plus B1 y3 plus C1 z3. Then in the second row, A2 x1 plus B2 y1 plus C2 z1. A2 x2 plus B2 y2 plus C2 z2. A2 x3 plus B2 y3 plus C2 z3. In the third row, A3 x1 plus B3 y1 plus C3 z1. A3 x2 plus B3 y2 plus C3 z2. A3 x3 plus B3 y3 plus C3 z3. So you can write lambda 1 x1, lambda 2 x2, lambda 3 x3, lambda 1 y1, lambda 2 y2, lambda 3 y3, lambda 1 z1, lambda 2 z2, lambda 3 z3 using the results. You can write your x1, x2, x3, y1, y2, y3, z1, z2, z3 is equal to lambda 1 0. So this is x1, x2, x3, y1, y2, y3, z1, z2, z3 multiplied by the matrix lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3 is equal to capital P multiplied by capital D, where D is the diagonal matrix. And it is nothing but lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So you can write AP is equal to PD, or P inverse AP is equal to P inverse PD is equal to D. The square matrix P, which diagonalizes A, is found by grouping the eigenvectors of A into square matrix, and the resulting diagonal matrix has the eigenvalues of A as its diagonal elements. The transformation of matrix A to P inverse AP is known as a similarity transformation. The reduction of A to a diagonal matrix is obviously a particular case of similarity transformation. The matrix P, which diagonalizes A, is called the model matrix of A, and the resulting diagonal matrix D is known as the spectra of matrix A. So there is an example. How can you have your diagonalization? Please see in the screen. So from tomorrow, I think we can start quantum mechanics. And you have any doubt in both of these courses, we shall discuss it at the end of the courses. Am I audible?
Yes, sir.
Thank you.
Sir, अरे मैं काटे तो रेडी
Thank you very much.
Thank you, sir.